Good to see you. So, yeah, this is the last presentation of the day, so let's hope we can make it really interesting to finish up. So I'm going to talk about threading and multi-threading on mobile devices. So why am I talking about this? Well, it's actually crazy to think about, but I've probably been working with mobile for more than 20 years. That sounds crazy, but as you see, I was the founder of Realm, which is a mobile database, and a lot more than that. But before that, I worked for Nokia doing mobile technologies. So it's been pretty crazy ride following the mobile technology all the way through. But today I want to talk about threading models. It's one of the most interesting topics for mobile because it used to be back in the days, Nokia and everything, that there was really no talk about threading on mobile devices. They were just too weak to actually really do multi-threading. But of course, today with modern devices like iPhones and all the new Android devices, everything is multi-threaded. It has to be. But working with multi-threading is really problematic. So, I mean, why do we care about it? Well, the first thing is, of course, that mobile apps are inherently multi-threaded. They have to be, because to make a responsive UI, you have to make sure that it only does the drawing of the UI. If you do like hard computations, you do persistence, you do all that stuff on your main UI thread, that would basically block the thread and the UI would not update. And you can say, well, hasn't it always been like that? Well, the different thing is that when you do a mobile app, you actually have the app in your hand. And people are interacting with the app directly, and the fact that it's something you have in your hand actually makes it feel much weird if there's delays, right? If you're on a web page and something like jiggles or jacks a little bit, or it's a bit slow, or you click something, it's slow to reload, it's just kind of expected. It's distant from you, it's on a screen. But the mobile device it's something that's right under your finger. If suddenly the things are slow, the app kind of stops for a little while, it just feels fundamentally wrong, and people will just say, okay, this is a crappy app, I'll just delete it and then install something else. So that's why every app is built around multi-threading. I mean, every modern app framework is built around that you have multiple threads, so you can take all the hard computation, all the persistence, all the stuff that could potentially block. You put that on background threads, and then you do the UI on the main threads. So it's just a given today that if you build an app, you have to deal with multi-threading. The problem, of course, is that understanding multi-threading is really, really hard. I mean, it's one of the top problems in computer science. How do you deal with threading, and how do you understand it? How do you make sure you don't get into trouble? And the kind of bugs you get from multi-threading those are the hardest bugs that exist to debug. I'll go into more detail on this later, but I mean, most other bugs you can kind of you can find them, you can recreate them. Threading bugs can be crazily hard to reproduce. So that's really why you want it. And the challenge here is that we have a lot of traditional ways we try to handle state with threads. And none of them really work really well. I mean, they're all kind of complex, they're error prone in different ways. So a lot of my work through these last 20 years, I've been looking at what are better ways? Are there better ways of doing it? What are the existing ways? And could there be different ways to do it that will help us in the future and now, of course? So that's kind of my dream, there has to be a better way. So, I mean, the first question when you start and you don't really know much about multithreading, you say, well, what is the problem actually? I mean, why can't I have objects today? Every modern framework is somewhat built around objects or structures, and you say, well, why can't I just use my plain objects? I mean, that's what I have in my programming language. What is the actual problem here? And of course, the problem is that these plain objects that you have in all modern programming languages are not thread safe. Basically, you can have something happen that called race conditions, right? You can, if you use these same objects on two different threads at the same time, things might blow up, and we'll go in a bit more detail on how that happens. But they're not safe to work with across threads. And on top of that, plain objects also have some other problems. First of all, they're not observable. And you say, well, what does that even mean? It means that you cannot get notified when they changes, which is a huge problem in the context of UI, right? Because when you build a UI, you really want to you want the UI to update as the data underneath changes, and you wouldn't want to kind of pull like do a diff against the objects all the time just to see if they changed. I mean, that would both be slow and cumbersome. You want to somehow get notified when the data itself changes so you can update the UI. And plain objects just don't really have any mechanism to do that. And of course, the other thing is that they're not persistent. And persistence doesn't just mean that you'll put, I mean, of course, I come from a database background. You say, well, persistence is you put it into a database, but that's not even necessarily the case here. It's more that with a mobile app, at any point in time, it can get shut down, it could crash, the phone could run out of power. Anything could happen that makes the app essentially shut down with no warning. And the modern expected experience is that, well, you start the app and you can continue basically where you left off. And at the very minimum, you should not lose any data when that happens. So the data you work with has to be persistent in some shape or form. And again, plain objects are not persistent. Of course, you can always read them, and then you can write them to disks, and you can write them to JSON files or to whatever you wanted. But that means you have to do it all the time. And again, if the app crashes before you get to do that, then you lost all that data. And the one like golden rule of good application design is you can never lose the user's data. Right? I mean, losing the user's data is just like the cardinal sin of app design. Like, no matter what goes wrong, you should never be able to lose or corrupt the user's data. So that means like plain objects are just not, they're just not really a good solution. And the biggest one that we really want to dive into now is the threat of race conditions. So race conditions, I mean, race conditions are really the most problematic part about multithreading. So what is a race condition? Well, a race condition is when the behavior of the program suddenly becomes dependent on timing. That it will work one way one day and it will work another way another day, and it'll depend on the timing of other things that are not related to what you're doing. A very, very simple example here, just to simplify it of a race condition. So we have a minimal program here that basically just say, I want to divide two numbers to get a third one. And of course, I want to make sure that I don't do a divide by 0, because obviously like that would crash the app. So I write my code and I say, well, if a is not equal 0, then I can divide with it. So this seems naively simple and easily to see is correct. And it is correct if you're on a single thread. The problem comes, what if there are other threads that actually have access to that same state? So you could have another thread that at any given point in time set a equal to 0. And since threads, they happen simultaneously. I mean, that's the whole point of threads, that things can happen concurrently. You can have this that in thread 1, you actually check that whether a is 0, but in the few microseconds that happens between the check you do and the operation you do, that value might actually have changed by an action on another thread, and you get a crash, obviously. And again, the challenge with this is that this is timing dependent. Again, if that a equals 0 had been like a few milliseconds before or later, then everything would have worked. And that is really the most insidious part about race conditions. The fact is that race conditions only happens when there's what's called contention. Right? So that means that when it happens when a lot of things happens at the same time. And that is problematic, because that means that they happen very rarely, which sounds like a really good thing. You say, well, it's a bug that very rarely happens. That's awesome. But it really is not, because what happens is that when you test your app, everything works perfectly fine. Because usually when you test your app, there's no contention basically there's not that much going on. You're just testing, especially if you're doing it with unit tests and all kind of things that you're basically doing like small tests back and forth, and you're kind of like just exploring the UI yourself. Whatever you do for testing, there's not that much happening. There's not that much data in the system. There's not that much going on. There's not much network activity. And in that case, everything probably works, because it's almost as if the first thread was just working on its own, because there's not that much else going on. So the chance that you're just going to hit the timing where things blows up, it's minimal. The problem is then that it goes out into production. You get out to like millions of users, and they start putting lots of data into the system. They start using the app a lot, and suddenly you start getting these weird bug reports of like inexplicable things happening out in the field, which there's no way for you to reproduce at home. You're just like, these values just don't line up. That is really the danger of race conditions. I mean, they're called like the worst of all bugs, right? And again, the danger is they might not show up until years after the code has been placed in production. And that really, really sucks. And they got this name in the computer science community of like being Heisenbugs, because they are non-deterministic. I mean, they depend, even the fact that since they're timing dependent, even the fact that you observe it might change the behavior. So you have a bug that every time you're running in production, like in production mode, it crashes, then you attach a debugger and then it works fine. Because the fact that you attach a debugger changes the timing of the system. So you add logging, and that also changes the behavior. Everything you do slightly changes the timing behavior, and it may or may not trigger the bug. So these are like the kind of bugs that just make everybody like pull out their hair, and you spend like months just trying to explore and find out, okay, how do you trigger this bug, and like how to reproduce it consistently so you can actually fix it. So I guess the core point of this is you really don't want to have race conditions in your code. If at all possible, it's so much better if you can design your software in a way that essentially makes the race condition impossible. Right? You don't want to risk race conditions in the middle of everything, and that really takes careful software design. I mean, you have to. There's one way of doing it, which is like really, really understanding multithreading and building everything around it. That's the hard part, and you can study many years to try to do that. Or you can hopefully work within frameworks and software that's well designed that actually prevents these kind of bugs from appearing, and puts in guardrails and makes sure that there's almost no chance of exposing these kind of bugs. So how do you avoid these kind of race conditions? So the classic old school way of doing it was with locks and mutexes and different variations, right? So, I mean, that's one possible solution. So what does a lock look like? So the classic lock is a mutex, which is a lock that can communicate across threads. So it basically means that only one thread can have a lock at any given point in time. So in this case, we have the exact same code, and as you see on one side, we wrap the whole operation with a lock. So both the comparison against zero and the actual division is within the lock. So that means that on the second thread, since we also have the assignment to A wrapped in a lock, it basically ensures that we get the timing we want, because the second thread will not be able to get the lock until the first thread have released it again. So there's basically no chance that this can happen simultaneously. It turns it into, instead of a concurrent operation, it turns this into a sequential operation, so that it has to be first one thing and then the other thing. We actually don't control the order here. In principle, the A equals 0 could happen before or after the what happens on thread 1. Again, that is timing dependent. But what we do know is that it can never change while within the lock, which is really what we want. We want it to never change while we lock. We want to have the guarantee of consistency. So this is all about consistency. What we see now happening on thread 1 is that within the lock, we have consistency. And that's within databases, we talk a lot about consistency, and that's the some people have heard about the ACID statement about the database have to live up to, of which consistency is one of the most important one. So the consistency and isolation, which are what we see here, is that with the lock, we both have consistency and we have isolation. But we also have problems. I mean, the whole point of doing multithreading is we want to be able to do multiple things at the same time. But if everything is wrapped in locks, I mean, you can only do one thing at a time, even if no matter how many threads you have. The lock every thread has to wait for the other threads to release the lock before they can do any work. So there's a huge performance impact if you're not really careful. And on top of that, you have other problems. I mean, the obvious one is you could forget a lock, then you're really in trouble. It might not be obvious from your code where you should lock or where you shouldn't lock. Because there's no requirement. It's not like you're going to get an error if you forget a lock somewhere. You just introduced a race condition. Sucks. So it's very dependent on programmer skill and attention. So as long as you do everything correct, it works. But if you kind of forget a lock somewhere, yeah, you got the problem here. And then there's a whole series of other problems that they're too coarse-grained, these locks. So usually you start having multiple locks, and then you start getting into what's called a deadlock situations, which is where you have multiple locks that depend on each other, and that can get kind of circular. So one lock depends on one, which actually depends on the same one again. And that means that you can never get the lock. They just wait for each other, and the whole app just grinds to a halt. So that's also a very well-studied problem with locks. So in general, I mean, locks are not that good a solution for dealing with multi-threading in modern situations. It's too slow. It just blocks everything, and they usually get too coarse-grained or too fine-grained. It's messy. It's really hard to get right. I mean, if in a huge code base, somewhere you're going to get it right. I mean, you're going to lock too much, too little. You're going to do some dependency that risks deadlocks. You're going to forget a lock. I mean, everybody who's done this kind of code knows that somewhere in a huge code base, it's just going to get wrong. And you still got these annoying race conditions you have to hunt down. And then, of course, I mean, it doesn't help you on the observability. There's still no way to get notified when the data changes. So no help there. So everybody hit into this. I mean, when you see this on every platform, and especially in the context of UI, where you have these multiple threads that really have to communicate. People tried locks, and it was just too much work. I mean, they still use locks occasionally for very specific things, but for like modern mobile apps, for the main interaction between threads, they're just not sufficient. These problems are just too hard. So in the process of this, people got a good idea. People looked at something called like functional reactive programming, or functional programming in general, and noticed something called immutability. So the idea behind immutability is that what if the data did not change? So the whole problem with race conditions is that the data can change depending on what happens in other threads. What if it couldn't change? What if you were like guaranteed that this data will never change? I mean, then there won't be any problems. So what does it mean that data is mutable? Because actually it does change. We know that. I mean, it would kind of suck to have an app where the data never changed. That would be a very, very boring app. Of course, data does change. So how do you give the illusion that it does not change? Or how do you basically cheat the processor to think, oh, this data does not change? And the idea behind immutability, which comes from functional programming originally, is what if instead of mutating, changing the data in place, which is what you do with plain objects, what if we instead just returned, and every time we made a change, we actually returned a new copy of the data with the new changes. And you can say, well, that sounds crazy. I mean, you might have a huge data set, right? And then if every time you do the slightest little change, there's like 1 bit you flip, you have to copy the whole thing. That, of course, that would be crazily slow and use all your memory and all kind of other things. And the people who did functional programming back time, they of course noticed that and thought of changes to that. So they did invented what's called like persistent data structures. Which basically means that instead of just copying the whole data structure, you are able to just copy the small pieces where the change happens, and then keep pointing into the old data structure for the rest. So that means if you're just flipping 1 bit somewhere, you're like a boolean, you change from true to false, whatever, you really don't have to copy very much data. I mean, you just have to copy the value that actually contains this, and then the parents of the dependency tree. And then you just return the new top pointer, and you got the new data structure. So on modern systems, this can be done very efficiently. It's basically copy on write. And that's how your file system probably works today, and all kind of parts of internally in the computer work today. And the cool thing about this is that, like, if you look at the illustration on the left, like if you look at V1 of this data structure, even though we create a V2 and then like time moves ahead, V1 does not change at all. So that means that you could have like hundreds of threads actually reading this V1, doing stuff with it, with no worries, even though that you suddenly have V2, V3, V4, like time just passes on, you get new versions all the time. And you basically don't have to worry about it, which is amazing. It gives you an entry to solve a lot of these problems. So looking at the same examples we saw before, we have these 2 threads. They both need to work on the data. But thread 1 has like the V1 version of this data. So it has the A, which is marked as A1 here, and it checks that is equal 0, not equal 0, and then it does its calculation. And there's no race condition, because even though that thread 2 is modifying it and creating A2, that does not affect thread 1, because it's still looking at the previous version. So magically, we fix the problem. Of course, there is one problem more, which is that the data actually did change. And the first thread cannot hang around until V1 forever. So the big question is, how do we, now that we have solved part of the problem, saying, okay, we want things to be immutable so they don't change underneath us while we're working with it. That is super important, because the moment that things can change underneath us, we have nothing. We're just open for race conditions all the time. But we still need to know when things changes, because the fact that even though we're looking at individual immutable snapshots, the world is moving on. So we have to make sure we actually look at the latest, at least most of the time, the latest snapshot, and get notified when new things happens. So that was also something that functional programming came into. So they came up with something called functional reactive programming. And reactive in the sense that you react on changes. So you're still functional in the sense that the data is immutable and you can do pure functions on top of it, all stuff, but you still need to react on changes. And you do that through something called streams. So that means that change is modeled as a stream of immutable values. So you can observe a state, and that state will change through time. But the only way you see that change is that the stream will emit new versions over time. So basically you start here at T1, and then you grad some, it'll emit T1, it'll emit T2, T3, T4. And you can sit as an observer and observe changes and say, hey, now there's new version, now new version. And obviously you can update the UI in response to that. There's a variety of things you can do in response to these changes. And the cool thing about having think of streams is you can start composing them. You can like zip streams together. You can do all kind of things with these streams. So it is a very powerful paradigm for data that comes in. And it got very popular. I mean, almost the pioneers of this was actually in JavaScript, interesting enough, where frameworks like React started using these kind of streams to compose the UI. And then the reactive paradigm got very popular, so you saw stuff like RxJava coming out, and like just about every platform had got a reactive library to handle streams. It's a very, very powerful paradigm, but it does also have its downsides. I think that is one of the things that most people are not really aware of, because right now this is like the popular paradigm. It's always interesting to look at the dominant paradigms out there, and then take one step back and say, hey, is this actually the best way to do things, or are we all just wrapped up in this is just a way to do it, so this is how everybody else do it, so let's just keep doing it. And it turns out that especially on the JavaScript side, people have been using this for a long time. You kind of start to see certain problems. So this is a fun Twitter post that I came up over that from a guy called Michael Westrate, who's funny enough is one of the guys who both created a library called mobx, which is an alternative to Redux and this kind of programming on JavaScript. And he also created one of the most popular immutable libraries called immer. But what he says here is like what would be an unpopular take opinion to have, because it's against everybody else's opinion. And he says, well, immutable data structures are an unnatural fit for things that are supposed to change over time. That is an interesting statement. I mean, what does he mean with that? Well, the thing is that there are problems with modeling state as streams. Because, I mean, they are not. I mean, streams are awesome for things that are stream-like. If you have input from an input device, you have streams of data coming over a socket. There's all kind of things that you're reading like from different streams. There's things that are natural stream-like, that are just values coming in that you need to process. And then there's a full state, a huge state that actually mutates over time, that you kind of want to model some way to observe and safely work with. And his lesson from being in the JavaScript world, which was far ahead now, that we're kind of copying right now in the mobile world, weirdly enough, was that with experience, maybe that's not the best way to do things. I think that's very, very interesting to look close at. So what kind of problems do you have with streams of immutable data? So one of the problems is that they're very prone to like over and under observation. So the streams are in some way, they're kind of dumb. The challenge with streams is that they conflate two things that are different. They conflate the state and the values. In the sense that if you have a huge object graph, all kind of objects, they kind of link to each other, which is what you have in the complex data structure, whether that comes from a database or from native data structures, whatever. You might have a huge complex object graph. You may observe a single object in this graph, and you will get a notification or a new version every time this changes. But the challenge here is what actually changed. Did the object you look at change, or did the state as a whole change? And you say, well, why do I care? I only care if the individual object changes. But the reality is you don't necessarily, because even though the individual object has not changed, its surroundings might have. Like all the object that it links to or that links to it might have changed. And basically with streams, you only have two choices. Either you do it fine-grained and you say, well, I'm only going to send an event when your specific object changes, which means you have no way to know that the environment around it changed, which might be super important. I mean, actually in the UI, you might be displaying something that comes from following a link or a reference or a pointer, whatever, from within the object, which might, and the target of that might have changed. Who knows? And you will have a glitch in your UI. The other alternative you have to say, well, I'm just going to send you like a new version every time. And that's basically, if you look at something like Room as a good example, as a database, that's basically the choice they do. They say, okay, well, we're just going to send you new versions every single time the state changes. We'll send you, even if the object have not changed at all. And then you get code like this. It's a very simple example from Room, was just showing that you get a user by its ID, and it'll give you like a flowable, and then you have to pipe that through a distinct operation, a filter, so that you filter out all the changes that are the same. Because again, Room will just keep pushing your changes, even if the object itself has not changed at all, because its surrounding have changed. So that pushes a lot of computation out to you. You don't have to do, if you don't do this, your UI will have to update far too much, which will suck. It'll make the app slow. But then you have to do all this, and you still have the problem that this kind of distinct until change means that the UI part that actually look at this, it will have an old version of a stale version of the object. And again, it might be value-wise equal to the latest version. But when you follow references and stuff to it, from it, references to other objects, they might be from a totally different state, which can give you like weird UI glitches. So you're kind of in this thing that the streams can just not represent this difference. So it's just not very fine-grained, and it does introduce both small glitches and unneeded work. And it's just like there's some kind of fundamental disconnect in what the stream gives you and what you really are trying to represent. But this is not the worst thing. The worst thing is that you can still have race conditions. The problem is that the state still does change. So in the most simple case, I mean, when you have your state as your model, and you ask for a version, it will give you the latest version of it, which is good. And you'll get an immutable version of this, which is even better. So that does not change. The challenge is when suddenly you need to work with multiple objects at the same time. So for example, here in this very simplified example, you start by getting one list of tasks, and then you get another list of tasks, and then you want to get the total. Well, again, the world moves on. The world never stops. So in between those two calls to get object, the state might have advanced, and both these objects may have changed. So that means that when you have my task, you have your task, and you try to like do some kind of aggregate operation between them. In this case, just adding the links together to get a total. The result you end up with might be totally incorrect, because they might have changed, one or the other might have changed in between those two objects were put out. And of course, there are ways around this. I mean, you could wrap this in some kind of transaction. Some libraries will allow you to do that, to make sure that you get them as one operation instead of two. But that's exactly like the original state, like the idea with locks in the original race condition presentation, that if you have to manually put a lock around it, I mean, you're going to forget it at some point. That's just natural. At some point, you're going to have an object, and you have it in your app already. You're going to need it to compare it with some other one, or aggregate some values, or follow some links, or do something else. And you will pull out a new object, and it'll be from a different state, and you have stale objects. So one of the big problems with immutability is the risk of stale objects. You might have a mix of, in the same operation, you might suddenly end up with a mix of objects from different states. Even the same object, sometimes twice from the same state. This can happen both through streams that kind of get out of sync, and suddenly they're not entirely coordinated about the state, and even more like in like standard UI code or code where you just need to work with the objects and you do your business logic, and then suddenly you have mismatched versions. And again, this is race conditions that are really problematic, because again, it usually doesn't happen. I mean, these are the kind of bugs you're not going to get any warning from it. You're not going to see anything happening, and it's not going to show up as a problem during testing. So that is deeply problematic because, again, most of the time it's benign. I mean, actually, the moment you start to notice this, you'll see it in many apps. You'll see small glitches in the UI where one part of the UI updates and the other one does not. Probably all seen that happen. And it just happens from one or two objects getting stale. And most of the time, it's just a benign glitch that kind of eventually resolves itself. Just one part being a little bit behind the other. And other times, you have some kind of calculation that just avalanches, and then it turns into a totally wrong value or crash. And you get weird bug reports that are just impossible to debug. So that really, really sucks. So to sum up here, like the problem with modeling data streams is it conflates state and value change without difference. It's very prone to over-under observation. You need to constantly refetch objects to make sure you have the latest versions. Something I didn't really get into, but it also lacks referential integrity, which means that it's really hard to find the same object again if it's deep down in the object hierarchy. If it doesn't have a primary key, then when you go from one version to the next and things have changed that might have moved around position, it's almost impossible. I mean, you can try to diff it, but that's a lossy process and might get the wrong one. But the really big one is the risk of stale objects. You might introduce race conditions that might cause crashes or just incorrect displays. So there must be a better way, right? And the question is, what if objects could be both immutable and at the same time observable and always up to date? I mean, it sounds like a contradiction. Like, how would that even be possible? But it is actually possible with modern data structures. So this is, again, the same examples as earlier, but with something we call transactional objects. So since every UI system today runs with an event loop, like the loop on Android, you can actually bind the immutability to the event loop. So you can have objects where within a cycle of the event loop, it'll be immutable, but in between it can move to the next version. So the benefit of this is that the objects are always functionally immutable. There's never any chance that the data can change underneath you. But at the same time, they will always be up to date. If not in the cycle of the UI, like immediately in the next cycle of the event loop. So the same examples we've done from beginning here, if we see this, we kind of do the same thing twice. And the first round of the event loop, we do the comparison against zero. And at the same time, on another thread, somebody's doing a transaction that updates the A to 0. But in the first round of the event loops, even though it happens at the same time, it's protected because the data is immutable. So it does not see that change happening. But immediately after, you have a second loop and you do the same thing again, but now it does see this change. But just like with the logs, we're guaranteed that the change never happened while we're working with the data. And that is the key thing, that you got this rock solid foundation saying the data never changed underneath me. It might change between the times I do things, but it's never going to change underneath me. I can always trust that my data is stable. And that's basically it comes from, of course, from database, the idea of transactions, but it's something you can apply directly to objects. And the cool thing about this is you have access to the full object graph. You can query millions of entries directly. You can just traverse the object graph freely. It's observable. So you don't have to do all these kind of weird things where you filter out things distinct. You actually changes so that the state and the values are differentiated between. So you can watch for changes and you'll get notified exactly when something changes, but only when it changes. But even if it has not changed, the object that you are using to draw your UI still is still up to date, and every link from it will point to the latest state. So you have decoupled this hard connection between state and values, so you can get the benefit of both. So that is super powerful. Of course, you don't want to do changes on the main thread, so you can still easily do changes in background threads. You can do these transactions that are asynchronous that happens on background threads. So all your writes happens on background threads. And if you do need a full immutability, like the old school immutability, you can freeze the objects, because the transactional objects are, I mean, we call them live objects in the sense that they are live and that they do change from the user perspective. They seem like plain objects, but they're just immutable in every context you work with them. But between contexts, they do change, so they are live. So that means that, I mean, if you want to do something on a long-running background thread, you should pass it a frozen version, so that it can gradually work with it and spend its time with that without worrying that it changes again underneath it. So in some ways, you have the best of both worlds here, that you can both work with things almost exactly as if they were plain objects on the main thread. They just update, you don't have to refetch them, you don't have to do anything, it just works. And at the same time, you can freeze them and pass them on to streams or whatever you want to do, and they will work exactly as immutable objects. So the benefit of transactional objects is that they work again with huge object graphs. This is actually important, like bigger than memory object graphs. This is something it's really hard with immutable objects, because you get a copy of it, and if you have to copy it into memory, so you can diff it later, it just doesn't work with data that's bigger than memory. With transactional objects, you don't have any of that problems. It can all happen. They're immutable while you're reading them, so they never change underneath them. But the moment you create a write transaction, they actually all become mutable within that write transaction. So you can freely work with them again, exactly as if they were plain objects, do all the modification you want, and the moment the write transaction commits, you have a new immutable snapshot. And they offer fine-grained observability, which is, again, super powerful to connect to the UI. They're always up to date, which is great. There's no need to refetch. And most importantly, there's no risk of race conditions. There's like guardrails around you that makes it impossible to create a race condition, because these objects you can never have two objects from different versions of the state at the same time. They will all advance together. So those are the pros. The cons, of course, because there's nothing that comes without cons, sadly, is that if you want to hand it to this data between threads, which you do want to do, you have to hand the objects over and say, either give it a frozen version or its own live version. So there are lots of easy ways to do this, but it's still something you have to do. The cool thing is that you will get it, compared to race conditions that can give you errors at like a year after you put it in production. If you try to access a live object from a different thread, you will get an instant exception telling you that, hey, you need to do a handover here. So it's easy to debug afterwards. So that's basically one of the approaches we support with Realm, and it was kind of one of the, based on my experience, one that is really, really powerful for building safe, fast apps in a way that's also has a lot of ease of use, how to do it. So going a bit quick, and then I really want to have a chance also to answer questions. So I want to thank you guys for listening. I hope there'll be some questions on details of this, so we can spend the last few minutes on that. If you're interested in trying this out, you can actually try these kind of transactional objects today in the Android version of Realm. You just go directly to MongoDB's Realm site. And right now we're building the next generation version of a fully native Kotlin SDK. So if you want to join us in building that, I will invite you to go directly to a GitHub project. It's all totally open source. So you can just join in and then follow along. Thank you, guys. So let's see if there's any questions. So we'll just wait a little while to see if there's any questions coming in. Otherwise, I hope that the presentation has answered every single question out there. There's nothing to worry about. I guess this is the last presentation of the day, so if people are a bit tired, I do understand. Cool. Well, let's wrap it up for now. I think I don't think there's any questions, so I'll just thank everyone of you to join in for joining in. It's been perfect. Oh, there's a few things happening here. There's still a question there. There's one here says like, does a write before read also pose a problem of race condition? And there's a bit of context here, so I'm not entirely sure I understand exactly what is meant, because that right before read can be many things. But yes, I mean, there's not a race condition if you. The problem is that if you write yourself and then you get the same version, the new version back after the write, then you should be up to date. The challenge is, what are you actually writing, and do you still have other objects that has not been updated to reflect the write you just did? That is the problem. So let's say you have a process, like a function that uses 10 objects, and you do a write to one of them in one way or the other. You might do this on a background thread, you might do it directly, and you get in return you get a new version of that object you just wrote to. That is fine. That object is safe. But what about the 9 other objects that you had, which are from the same state? They are now stale versions. They're from a different version than the object you just did the write to. So unless you make sure that you go back and refetch all those 9 other objects so they match the same version, then you do have a chance of a race condition. So I hope that answers the question. If not, you're welcome to ask with more detail. Very cool. Again, I will really encourage you guys. I mean, this was a very short introduction just to the cool ways you can work with multithreading if you kind of think different about the data structures. I'll definitely encourage you to try to download Realm and play around with it. And again, try to join in and look at the new Kotlin SDK we're building, which is, I mean, the original Android SDK also works with Kotlin, but it's built on top of the Java SDK. So we're now building a fully native Kotlin SDK, which is pretty cool. So you can join directly into that work and follow along in the GitHub repo. And there's also your chance to influence the design of it. It is a full open source project. Cool. Cool. Well, thanks for the one question, and thanks for joining the presentation.